In this video, which I have sent to you, I have uploaded so that you can check in your uh, classroom uh, place. There's an analogy between what is an hydraulic system and an electrical system. The analogy consists that uh, uh, the stream of water is like the current, the electrical current. The pump is like the battery. The piping is like the wires. The reducer in the piping is like the resistor, and the water wheel is like the inductance. Uh, the, the inductance as the water wheel, they oppose to the change. The water wheel opposes to the change in the speed of the water because it has inertia. Also, the inductor opposes to the change of current. The same is it if it is growing, if it is increasing, than if it is decreasing. In both cases, there is a change and there is an opposition from the inductor. So, analyzing the circuits, what happens at the first moment when we close the switch, there will start a current. I will signal from the positive to the negative. We know that electrons go in the opposite sense, but the current actually, and the conventional current is from plus to minus. So in the first case, as it is starting a current, this is it is opposed by the inductor and will take a long time, relatively long time, to start flowing current here. So in the beginning, all the current goes through the lamp. But then it starts to grow the current, and it is creating a magnetic field until it reaches a maximum value. When it reaches its maximum value, the current through the inductor is constant. So there is no change. In that moment, there is no opposition at all. So it is less opposition in the inductor than in the lamp. The lamp has a resistor inside, it's like a filament. So it prefers to go through the coil, and there will be no light on the lamp. And here we can continue, but if we interrupt this flow from the battery, acting this switch, opening the switch, then the energy stored in the coil starts to produce a current that will go through the lamp, and it will continue. It's due to the magnetic field that has been stored, and then that magnetic field produces a current uh, and it dissipates in the lamp. But immediately it starts to diminish the current so that the lamp intensity will be lowering little by little until it finishes completely. Then in that case, we can say that the inductor has discharged or has liberated its energy. So it stores energy and releases the energy, and that's the function of the inductor. Okay? Inductors don't like change. They want to remain the same. When current increases, they try to stop it with an opposing force, an electromotive force that produces an opposing current. And when current decreases, They also try to stop by pushing electrons out to try and keep the same as it was. So the same is if it is increasing or if it is decreasing. Meanwhile, there is a change, there is an opposition. Okay, so what happens? We know that the, the current in the coil is not instantly flowing, but it is gradually growing, gradually increasing until it reaches its maximum value. The maximum value will be the value of the voltage E divided by the resistor R, because at that moment the resistance here is zero, because there is no position at all. It's like a plain wire of copper with very little resistance, much less resistance than the filament resistance. So uh, here we consider only the resistance value, and we have here the steady state current. We call it steady state because it's constant. But after a while, we can release this energy, as we saw, and it will follow this pattern. Also, is slowly, gradually decreasing, and this is there is a mathematical formula that defines this pattern and also this pattern, and it is depending on the what is called the constant of time. The time constant symbolized by the letter tau. It appears here, letter tau. TL means the tau of the inductance, the constant time for the inductance, which we will see in the next uh, slide. Okay, that's the same figure. The time constant tau for capacitors and inductors. The time constant tau is the time at which a capacitor or inductor can reach approximately the 63% of its full charge or the 37% of discharge. As we can say here, 63% 0.63 of the voltage. And here 0.37 of the discharge in the same amount of time, which is called one constant of time, 1 tau. The complete charge or discharge happens in about 5 tau. That means that after 5 time constants, 5 times the, the time constant, it will be complete the charge or the discharge. It is not properly scaled here, but when we have here 5 time constants, we will have a steady state value. And in this case, we are talking about the voltage in the coil, the discharge from the value of initial voltage will be discharged with this same pattern and will be finished about after 5 time constants. No? Well, what is the time constant? For RC circuits, RC circuits are circuits that are made out of resistors and capacitors. And L are, los llamados bien, RL circuits are those that only have inductors and resistors. but the time constants for each one is like this. For a capacitor, the time constant is the multiplication of R times C, the resistance times the value of the capacitance. For an inductor, the time constant is L, the value of the inductance, divided by R, divided by the resistance. In those cases, it's a number, it's a quantity of time to happen here. The time constant is a measure of how fast can be charged and discharged a capacitor or an inductor. Consider the following RC circuit consisting of a battery, a resistor, and a capacitor. The voltage in the capacitor's plates is charged according to the following equation. This equation, well, actually this graph is not for a capacitor, it's for an inductor. Well, in the next slide, remember these two equations, but we will see here in this next slide. Okay. In this case, we will analyze a simple circuit, RC circuit, RC, resistor capacitance. We have a power supply, it is a voltage E, in this case is 12 volts. We have a current from here to here, and that is the conventional current, but we know that the actual flow of electrons is in the opposite direction. Okay? Well, but we have a switch. I don't know if you can see also in this moment, when it all starts, we will call it the zero moment. The switch is open. Then we will have the first moment when the switch 1 is closed. We can see a red line here that symbolizes that first moment. At that moment, at closing, the voltage is 12 volts in the resistor, but the voltage across the capacitor is 0 volts because we are here in this corner. This is the moment just starting. We have no voltage here. We are in the zero. We have 0 volts of charge. And of course, the current here is 0. But we have this equation that defines the value of the voltage depending on the time. So it says that the value of the charge in the resistor will be the value of the initial voltage, that is the battery voltage, in this case is 12 volts. It will be multiplied by this subtraction, 1 minus the number E to the power minus T divided by RC. We can put also here minus T divided by tau, because RC is tau. Tau equals RC for a capacitor. So we multiply the value of R and the value of C. We obtain the time constant. So this equation we can figure out in the number of time constant. So at the first, when we have the value of one time constant, this equation means that we are dividing, where is the equation? Is tau, because it is T equals tau, or I mean T equals RC divided by RC, that is 1, the division of the same quantity, and but this is a negative sign. So this is will be subtracted from the unit 1 and multiplied by the value of the voltage. Let's do the first. Do you know how to manage the exponentials with the letter E? Look, I will share you for a moment. I will, well, for the moment, just believe me. For 1 times 1, the value of this expression is 63.2 before multiplying by 12. When we multiply it by 12, it is 7.58 volts. But what I want to tell you is for the moment time equals 1, tau equals 1, we have about the 63% of the charge here. We have 63%. When we have 3 taus, 3 time constants, we have 95%. Okay, 3 times. We have 95% of the charge. And when we have uh, when we have 5 time constants, we have 99 time constant. You know, it is almost 100. As the Chinese says, you know how do we say 99 in Chinese? No pueden hablar, ¿verdad? I will write it down. It is, Chinese say it is kachi chen. 99 is kachi chen. So we have here almost 100. So these 3 values are more important. But we can have a very detailed graph table, and then make the graph. For the discharging process, we have a similar equation. But we have this. I move the for the second moment, we close this switch and disappear the voltage source. So we will have here only a capacitor and a resistor, and it will be discharged like this pattern. It will start from 12 volts, which is the value at what it was charged here. It reached 12 volts. But then we can call it V0, like the initial value of voltage. So it will start decreasing. At time 1 tau, it will decrease 36.8%. At point 3 taus, it will descend to the 5% of the voltage, and at 5 taus, it will descend to 0.7% of the value. We multiply this by V0, we will have these voltages 442.6 volts and 0.08 volts. That is 80 millivolts. 80 millivolts is not 0 volts, but it's very, very low voltage in comparison with 12 volts. Okay, it is almost zero because this is an asymptotic curve that will continue for a long time, approaching zero, but not becoming the real zero. The mathematics. In the practice, it will come to zero after five time constants. Okay, that is for the capacitor. Uh, for this, uh, I put I made it a mistake here. I should put this resistor in the left side of this branch, but it is a circuit that I will send you later because I want you to do a simulation applying these equations, but doing it in multi-sim or in live wire. Okay. In this case, I have, well, later, before that, let me see. Okay, let me show you this. Are you still there? Who has a, who can make me like this? Try to speak and do like this so I can see you, that you are there.
Hola, profe.
Okay.
Hi.
Okay, you were listening. Were you paying attention? Uh, Now I will share with you uh, an Excel simulator that I made for the capacitors, and I will share it with you also. Let me. Okay. Now I put, this is another example, but this is a very similar. I should, I mean, it is the same capacitance circuit, the same RC circuit that we were seeing, but we have different values because in that circuit, I make the omission that I didn't put uh, how much was the capacitor and how much was the resistor. And even here, I didn't put the resistor. So I will put here. just for the initial example. But we can change here the values because it is alive. We can change the voltage. We can see here for the voltage it will reach to the value of 11.1992, for example. It's almost 12 volts. And also here the value starts at 2 volts because V0 is 12 volts. What what I am doing is just calculating. This is the value of tau. It is for the no, it is wrong. I made something wrong because it is no. I know I had made voy a poner aquí. Maybe I will correct properly, but it will be here. 50,000. It will reach sorry. It is I made something wrong. Oh, it's okay because here we have the voltage. Okay. The tau, this is what is wrong. What that the value of tau is 26.8 seconds. It's the value of tau in this case. So if I change these values, it will be longer or shorter the shape. But here is the formula. It's correct here. And for the decreasing is this one for the capacitors. Okay. And for the inductors, we have the same situation here. We have 12 volts, resistor 20 ohms, inductor 1.6, and we apply the same formula. You know, the steady state value of current is E divided by R. So 12 divided 12 divided by 20 is 0.6 amperes. Okay, so it will come, I will charge here from 0 to 0.6. It comes from 0 to 0.59595. Okay, and for the current discharge also starts from zero point 0.6 and comes to 0, which is here 0.004. So it would be 4 milliamperes. Starts in zero point 0.6 amperes, 600 milliamperes, and finish with 4 milliamperes. But it is very close to 0. Okay? I hope you have understood this, because you will have to make a simulation with this circuit, but I will change this resistor to here. I will ask you to do the simulation. I know about the time. I will check the list again.